In two separate videos, I'm going to compute the electric field produced by a point dipole. By point dipole, I actually mean any kind of a physical system, like a molecule, for example, where the dipole moment is known, but we don't know anything about how small that dipole is. So basically, the size of the physical system in here is negligible compared to the other length scales that we are thinking about. So first, let's state this. These are the electric field lines produced by this kind of a dipole. So every field line starts from the positive side of that dipole, the positive pole, and then goes around the space and then reaches to the negative pole. In any case, that means that at any point in here, the electric field has some kind of a direction, which basically makes the problem a little bit more complicated for us. But there are two special places where we can compute the electric field easily because we have some idea about what the direction is. The first one is this point. That's basically the symmetry axis of the dipole. So if you just rotate the dipole around this axis, then the dipole moment is not going to change. In any case, at this point, it appears that the electric field is always along that direction. And the second point is basically on the plane, which is perpendicular to this dipole moment and passing through the dipole. So in here, the electric field apparently is opposite to the dipole. So at these two places, it's actually quite a straightforward exercise to actually compute the electric field. And that's what I'm going to do. So these two problems are about these. So this is the first problem that I'm going to solve, and then I'm going to solve this problem. But let's start with this one. All right. So we have a point dipole in here. So the first thing that I'm going to do is to basically model this, basically think of it as at least 2 point charges separated in space. So I'm just going to take the simplest model, basically 2 point charges. So that's what I'm going to do. I suppose that there are these two charges, plus q and minus q, and they are separated by a distance d. So the dipole moment is essentially q times d. And I'm going to take r as the distance from the midpoint on the line connecting these two charges to the point in question. Right, that's that distance, and we are assuming that this distance between the charges is much smaller than this length scale in here. All right, so I'm just drawing an exaggerated picture in here because these kind of pictures helps us thinking about the problem. We can draw some things in a clear way, so therefore this is the reason why I prefer these kind of pictures. In any case, this positive charge is closer to that point, so therefore the electric field produced by the positive charge will be bigger and pointing towards right. And the negative charge is farther, so therefore the electric field produced by the negative charge will be a little bit smaller in magnitude. But these two electric fields are opposite in direction. Okay, what we need to do is basically add up these two, right? This is essentially the superposition principle. So the electric field produced by the positive charge plus the electric field produced by the negative charge is the electric field that we would like to find. So we have to do some kind of a vector addition in here. Or if we have some kind of an axis, let's say that the x-axis is pointing like that. If we have an axis, then I can do the same calculation with the components. So I can add up the x component of these two electric fields and then obtain the result. So just keep in mind that what we need to do is an addition. We don't subtract these electric fields. We are adding the electric fields because it's the electric field produced by two different point charges. So superposition principle tells us that the electric fields themselves are always added up, but one of them is negative. So this one, for example, because I have chosen my x-axis in the positive direction. In any case, let's quickly do this. The electric field produced by the positive charge at that point, so I know that that distance is r minus d over 2, so therefore this is 1 over 4 pi epsilon 0 q divided by r minus d over 2 squared. Let me place a plus sign in front to explicitly state that this is positive. And I'm going to add this to the electric field produced by the negative charge. So I know that this electric field is pointing towards left, so therefore it is a negative component. I can explicitly put the negative sign in here, or I can just put it in front of the charge expression. It doesn't matter. So in this way, this expression is quite similar to that one. The only difference is that the charge is replaced with minus q. So we have r plus d over 2 squared. Okay, since I have done this part earlier, let me do this quickly. So this is like 1 over 4 pi epsilon 0 q, and then we have the difference of 2 squareds. Right, so I'm just going to compute this part only. So I just take it inside a common denominator. So we have the difference squared divided by r squared minus d squared over 4 to the power 2. You can easily see that the numerator is basically equal to 2r times d. So in any case, so the final result is this is exact. So that's 1 over 4 pi epsilon 0 q multiplied with 2rd divided by r squared minus d squared over 4 squared. So the important point in here is that at some point we need to use the fact that d is much smaller than r. But when I'm deriving the expressions, I postpone this approximation to the very last stage until I see the point where, where basically I obtain the dipole moment expression. So I know that in the numerator I have charge, and d, charge multiplied with the distance is equal to the dipole moment. Once I obtain that expression, let me do it like this. That's 1 over 2 pi epsilon 0 r times the dipole moment divided by r squared minus d squared over 4 squared. Once I obtain this expression, I know that the electric field should be proportional to the dipole moment, right? At this point, I can take the limit where d goes to 0. So therefore, basically it tells me that I can neglect this d squared over 4 next to r squared. So as a result, I just replace this with 0 basically. So in that case, the electric field is equal to 1 over 2 pi epsilon 0 p divided by r cube. Or I can put write this thing down in the vector form. Right, that's p divided by r cube multiplied with the I unit vector. But in any case, this is also equal to the dipole moment. And so as a result, let me then put it down like that. In any case, coming back to the original question, so the electric field at that point can be written as in a vector equation. So the electric field is basically equal to the dipole moment divided by r cubed times this prefactor in here. I can express this as a vector equation like that because the dipole moments vector and the electric field vector are parallel to each other.